Okay, so we're talking about classification, folks, and in doing this, we're moving forward um, into methodologies and into the machine learning component. So I'm going to share my screen real quick, and we're going to start with a little bit of a high-level overview, and then we're going to talk about some of these concepts at the beginning. We're going to tie into things that we covered in the fundamentals. So classification is just that. It is a task to try and classify things, to try and determine what class an observation belongs to. And when I say classification, we could have a binary classification, like a positive or negative prediction, or a prediction of survived or not survived, churned or not churned, right? And our classification can be multi-class as well. Is this A or B or C or D or E? Okay, so high-level overview of machine learning is pattern matching, essentially. And what I'm going to zoom in on, this may seem like an oversimplification, but looking at the questions that our data science methods can answer, it really boils down to one of these 5 questions. Regardless of the algorithm name or anything else, classification is going to help us make predictions on if this new observation, if something we're looking at, a specific observation, like a specific individual in a telco churn data set or a specific employee in an HR data set, is this new observation A or B? Or is it C or D or E or something else, right? So we're trying to classify something, and our outcomes could be binary, or they could have multiple categories, right? In the case of something like handwriting recognition, we would have as many outcomes as we have handwritten characters, right? So these questions will help us frame things, and I encourage you all to put these on a note card or write these 5 different questions down, because they're really boiling down a whole lot, really boiling down an awful lot of machine learning and data science into 5 questions. So is this thing that we're looking at, does it belong to A or B or other classifications, or C or D or E? And the ability to answer that question about a single piece of data or about multiple data points is classification. And we're going to have all kinds of different classification tools in our classification toolbox. But overarching, the idea of classification is to classify things, right? And we're trying to classify outcomes on new data, right, based on training data. Another big picture question that data science methods can answer is how many or how much of something, right? And there's various types. That's called a regression. And there are different types of regressions out there. We'll cover that up, obviously, when we get to regressions. But all of those different types of regressions are trying to answer the question, how many, like counting or making a prediction of counts, or how much of something. And definitely encourage you to write this down, these 5 things down. Regression and classification are both supervised algorithms, meaning, or both supervised learning tasks, meaning that we have some sort of training data. And with that training data, we know what the answers are already, right? That's how we're able to do some pattern matching in general, is we figure out what the existing patterns are for the existing labeled data. Another question that our data science methods can answer that does not rely on labels or answers in the training data is what groupings exist in the data already. And in the material that we have in the curriculum, that's going to be covered by clustering. And clustering is really looking for similarities between things across multiple dimensions. And so clustering is looking to group things based on similar features or similar measurements. And there's more to this concept of what groupings exist in the data already than just clustering. But really, when we look at things that are similar to clustering, like like dimensionality reduction, that sounds really fancy. Dimensionality reduction, it means going from more columns to less columns in your data frame. Super fancy, right? Really, what's going on is trying to determine what groups exist in the data already. To the question of what should we expect to happen next, that's where time is part of the explanatory process, or time is an explanatory variable. And that's when we'll be working with time series analysis, right? If we're looking at uh, library fees for how long you've got a library book overdue, the outcome is a function of time, right? And some things are nice clean cut functions of time, and other things could have an ebb and a flow or a seasonality, and we're going to talk about that when we talk about time series analysis. A fifth question that our methods can help us answer is this weird? Is what I'm seeing weird? And in a nutshell, that's anomaly detection. And so in one way or another, if we can turn a business question or a research question into one of these kinds of framings, how many or how much? Is this A or B or C or D or E? What groupings exist in the data already? Different than classification, because that's looking for existing groupings. What should we expect to happen next? What are the most likely outcomes? And is this weird? These 5 questions, folks, are really the list of what we can work with, right? Kinds of answers we can produce. And based on the type of question that you're trying to ask of your data, right? And based on the kind of data that you have or the kind of data that you want, that determines what kind of tools we'll be using here, okay? This specific, like 5 questions that data science methods can answer, this is a rephrasing of some material from Microsoft that boiled down very similarly. So we're just trying to make things more approachable. We're not talking about crystal balls here. We're not talking about incantations or magic or inaccessible mathematics. We're talking about the ability to answer these 5 questions, or one or more of these 5 questions, depending on your scenario. Okay. So if we're trying to predict miles per gallon in a vehicle or miles per gallon in an engine, that's going to be a counting question, and that'll be a regression, right? If we're trying to classify, if we have some sort of definition of what good gas mileage is and bad gas mileage, that's like a binary classification. We might use a classifier there, right? So this whole module, we'll be spending about a week on lecture, and then I don't know if a whole week on the project, but yeah, is this observation A or B or C or D or E? Classification will be our intro to ML. Okay. So what are these classification algorithms? I mean, we could make our classification algorithms we have a variety of different classification tools, but they all share something in common. All of our different classification tools are doing what's called a supervised learning. And supervised learning is not all of machine learning, but it's quite a bit of machine learning. Anywhere where we're using data where we have the answers, or data where there's labels already, is supervised, right? So that means that we're going to train our data. We will train the algorithm pick up on patterns based on data with existing answers or existing labels for the outcome. And the big idea, the big goal here is that we're trying to train on our training data with labels and answers so that our algorithm gives us back a decision rule. If this, then that. Think about it like an if this, then that, or if, else if, else if, else if, else if, right? So if we can produce a decision rule with our training data, then that decision rule we can use to classify all of our future data. Right? Hopefully our models are good and valuable. They don't have a lot of falses, right? Like false positives or false negatives. But really that decision rule is what the model is giving us back. And I'll give you an example of that. In the diagram right here, at the very top, I've got an example of a flow of what I would call classical programming. Classical programming is things like, my first example is TurboTax, right? The TurboTax software takes in a set of rules. In this case, the rules would be tax law, right? Tax law for anybody's given circumstances, and based on their state or country. And then the data that we feed in there is your specific information or my specific information. Whoever the user is, it gives that application their specific data. And with classical programming, those rules are coming from law, like tax law, or they could be coming from business rules, right? When a user signs up for the newsletter, automatically add them to the newsletter email, right? Pretty straightforward. This is the realm of web development. This is the realm of most software development, almost all software development except ML, where we have rules that are coming from either the world or the business or what the customer has asked for, and we provide in data, and then we get answers back. At the end of TurboTax, you know what your expected tax return will be, right? And classical programming, the same, like classical programming applies with video games as well, right? Anything that's not like the rules for how the game plays, right? Any kind of game takes in the rules, the data, produces the answers. Classical programs. Now, machine learning, on the other hand, is a little bit different. And with supervised machine learning, we're trying to learn a set of rules given a large amount of data and labels of that data. And a classic example of this, one of the first machine learning products in use in business and in the world, came about in the 90s with handwriting recognition. Handwriting recognition from the United States Postal Service, super high-tech outfit at the time, actually. It would be very easy to write a classical program to recognize to recognize my handwriting, right? But then when we had somebody like we get Justin in, then we'd have to teach that classical program, okay, these are all of Justin's handwriting kind of habits, right? Or inflections and things. And so we'd have to make a new program for every individual if we were trying to recognize each individual's handwriting. Well, what we know in our lived experience is that there are a set of rules that govern things like handwriting recognition, right? And that while each one of us will have a slightly different version of the number 7, there's enough similarities that if we have enough data and enough labeled answers, we can produce a set of rules that will recognize somebody new's handwriting. And in a way, I'm going to use a quote here for this, how machine learning is producing a set of rules based off of data and answers. The idea here is automating the ineffable, right? Automating things that aren't easily written down as a set of rules. Facial recognition is kind of challenging, right? Or did you shave since the last time or you did like the facial recognition? Are you wearing glasses this time, right? Classical programming, if something is outside of the rules, it's not accounted for, right? But if we have enough training data, then ideally we're looking for the set of rules that we can use to make predictions off of future data. And in this way, supervised machine learning, that sounds like a really cool like vocabulary term, supervised machine learning. I'm gonna use a term I'm stealing straight from Cassie Kosakov. She's over at she's a lead decision scientist at Google. She calls supervised machine learning, her term for it is thing labeler with examples. Thing labeler with examples. I mean, this is cutting edge technology, right? The math goes back to the 1920s. The first implementations of machine learning have been around since the 50s, if you can believe it. But really, supervised machine learning is a thing labeler that runs off of examples. So you got to have good examples is the goal here. Okay. So questions at this point, big picture questions on questions our methods can answer. Any questions on this kind of diagram here of what is supervised learning and how is classification and why is classification a supervised learning task? Thing labeler with examples doesn't show up on a lot of Harvard Business Review articles on machine learning, but that's what it is. It's a thing labeler with examples. All right. So let's talk about some of our main ideas here. What's the big idea? Well, with classification, like we talked about, we're using labeled data. That's where we have the answers to train algorithms to classify future data points, right? So I talked about this idea of a decision rule. The decision rule is some sort of boundary, right? It's a boundary between sets of points, sets of data points. So let's take a look at this example right here. We have two different features. We have the size of an observation. We have the color of an observation. And we also have labels for the training data. So all of the data that's on the screen except for the blue X was part of our training data, right? And what we're seeing in this decision rule here is that apples and oranges exist across the same exact spectrum of sizes. They have the same range of sizes. And so size doesn't seem to be a determining factor here. But if we draw a boundary, and how do we draw the boundary? Well, we already know that the red X's are apples because we have labels for our training data. We know that the orange X's are oranges because in that data frame, we would actually have an outcome or a fruit type or species or some sort of some sort of piece of data that tells us what the label is. And by drawing this decision rule could be a straight line, it could be a curvy line, it really is going to be a function of the labels on the data. And so when we get a new piece of information that its size is about in the middle, but it is very orange, it is more orange than red, then our decision rule is going to say, oh, that's most likely an orange. Aren't you glad I didn't say banana? And this is a really simple example. Like, folks, this is a dead simple example, but this idea of a decision boundary, whether if it's a straight line or a curve, the decision boundary is a function that's cutting some space up, right? So this is a super simple example. Let's see if I can't find sklearn classification. Let's find something that's a little bit more sklearn classification example. classifier comparison. Okay, so on sklearn, sklearn is a it's a machine learning library we're going to be using a lot of for classification, regression, etc. And so let's take a look at our input data. We have some red dots, some blue dots, and the idea is we're trying to classify if a dot is blue or red. And notice with these different types of classification tools, whether if it's nearest neighbors or a decision tree, see how the big idea here is about establishing a boundary. Regardless of the different type of model you may or may not want to select here. And we're going to cover a lot of these models. There are more models that exist in the world than we have time to get into. We're going to cover the big ones, like nearest neighbors and decision trees, random forests. And so notice each one of these different models is taking a different approach, right? These tree-based approaches like a decision tree or a random forest, these tree-based approaches are drawing horizontal or vertical lines, where some of these other models are drawing curved lines. But always and forever, what we're trying to do is get a decision boundary so that we can use this decision rule on future data points. That's what it is, folks. That's supervised learning. In a nutshell. Right, and if we were looking at something like telco churn, where we have more than just size and color, we will be able to make models on many dimensions, on many different features, like charges or their add-ons, right? And we can classify if we think that, or if we will predict that a customer will churn or stay. That's a nice binary classifier, is customer churn, right? Questions so far? Thoughts, comments? All right, let's keep on going. It is entirely possible to have multi-class classification. We do it all the time. Instead of just apples or oranges, if we had data points that were apples, oranges, and bananas, we would have a 3 spaces here, right? Okay, so there's some vocabulary that we need to talk about. If we're talking about a classifier, that's an algorithm that maps the input data to a specific category, right? The category as in a class. The classification model itself is a series of steps that takes the patterns of the input variables, generalizes the pattern. When it generalizes the pattern, that model is making a decision boundary, right? That's how that process of generalization works. As soon as our model draws the decision boundary, we have a way of classifying future data points, right? So generalizing the pattern means making our decision rule. And then we apply that decision rule to our new data to try and predict the class. The term feature we've used quite a bit before. A feature is a column in a data frame. Another way of looking at it is a feature would be an independent variable, and it is a measurable property, right? If we're looking at the telco data, the telco churn, the churn or not is the label, and then every other feature that we look at is a feature, right? And our features could be like the demographics of the customer. Are they a family user, individual? What are their current charges? What are the different items that they've purchased? Okay. The real goal here is to try and find features in our exploratory data analysis so that we're building models based on better features, right? Features that are more reasonable drivers. To Go back to the question that Maggie asked this morning, what's driving the outcome, right? Not all features are going to be equally weighted. So that you've got the lingo. If you're classifying a yes or a no, or a pass or a fail, churn, not churned, any kind of binary yes or no is called a binary classification. And anything that is more than that, so C or D or E or A or B or C or D or E or F or whatever, and we can have a whole bunch of outcomes, is a multi-class classification. Okay. So some of the more common classification algorithms are logistic regression, which we will be covering. It is technically a type of regression, but it is a specific type of regression that's built so that we can classify things. We'll be working with a decision tree. We don't have a specific bit of curriculum on naive Bayes, but once you get the pattern with one model, you can try out new models really, really easy. sklearn makes it very easy like that. We'll be working with k-nearest neighbors and random forests as well. And there's lots of other specific classification tools, like a support vector machine that's able to draw curves between spaces. Stochastic gradient descent is a mouthful, but that is another type of classification. And then we have some type of boosting algorithms like eta boost, bagging, and gradient boosting, which are ways of trying to juice your results a little bit. Okay, so when we start looking at our data, in order to make in order to do any kind of ML, especially classification, all of our features need to be turned into numbers. Okay, and we'll be going through some specific ways of doing that, because our models aren't going to be, our classification models and algorithms aren't going to be working on things like strings. They're going to be working on numbers, right? Because when we're talking about things like a decision rule that's based on the distance of known correct answers, then we need to make sure that our calculations are happening numerically, right? So we can't have any strings hanging around. Our categorical features, so our features that could be strings, or could be things like zip codes, right? Or our discrete features, those need to be turned into numbers as well to represent those categories. And we will be going through that. It's basically a process called encoding, where we take whatever strings we have or whatever categorical data we have and turn that into numbers, so that the model can train on numbers, and then we can decode that information and turn that back into strings, so that we can make heads or tails of it, right? Just like heads or tails, it's easier to represent heads or tails as a 0 or a 1, right? Our continuous features, so our features that are numeric and have a lot of precision, and there's no definite boundaries, we will most likely need to scale those, so that we're not comparing different units, like dollars to centimeters to age, as is one of the main reasons we'll scale. This is not the lesson on scaling features, but it is a good idea to scale your features. Again, so that we're not comparing dollars to centimeters to age. Strictly speaking, however, and this is so important, does your ML model rely on distance? And almost all of them rely on distance, which means we're going to scale almost all of our ML models. The one space where we have models that don't rely on distance, we're measuring distance between data points, is anything that's tree based. So all of our classification algorithms and regression algorithms that are using distance, we need to scale our data, or your results will be really weird, or even garbage. The one place where we don't necessarily need to scale, strictly speaking, still, it's not going to hurt you. But if we have any sort of tree-based algorithm, like a decision tree or a random forest. Okay. So let's see. Awesome, awesome. The next little section here, I'm gonna break down just high-level overview of a couple of different models. So we'll take it from the top with a logistic regression. We'll introduce this later in the modeling section. It is used to predict binary outcomes, and our output could be a value that's between 0 and 1 that represents a probability of one class over the other. So a logistic regression is a binary predictor, and it's got a lot of things going for it. It's interpretable, meaning that it's good for understanding the influence of multiple different features on our outcome. It's pretty flexible, um, pretty easy to implement the logistic regression. It's very efficient. It's not requiring a lot of computational resources. But on the con side, logistic regression, it's not necessarily one of the top performing algorithms, but it's good for getting things out the door. And we need to remove attributes that are uncorrelated to the output variable or correlated between each other with logistic regression. Like nothing's going to be all pros. There's always going to be some sort of trade-off, right? So logistic regression is a little similar to a linear regression, except we're getting odds. We're getting probabilities that an observation is one value or the other. I think the quintessential classifier in my mind's eye is a decision tree, which is a little different. A decision tree is kind of like playing 20 questions with your data. Y'all remember the road trip game 20 questions? Or the parlor game 20 questions. I'm thinking of something, and is it an animal, vegetable, mineral, all that kind of stuff. A decision tree is doing that with your data and with your labels to try to arrive at the right outcome. In decision trees, we can do binary or multi-class classification. And each node in that tree represents a single input variable at a split point that is making a classification. So decision trees actually look like this, where we're drawing either a horizontal or a vertical line based on the feature, where we can find a good decision rule. Okay. By their nature, if we're not mindful with our decision trees, these will become overfitting machines. They will learn the training data perfectly, but not generalize very well to our out of sample data. So we need to make sure that we're not making decision trees that are super deep. Like if we play 100 questions, you're going to get it, right? But 20 questions is different than 100 questions is different than 5 questions, and we'll talk about that a little bit. Actually, at great length, we'll talk about how to make decision trees that are more easily generalizable. The pros of a decision tree, very, very simple to understand, very simple to visualize, not as much data preparation as some of our other models. Pretty good performance. There is a high risk of overfitting, and overfitting is the process of where the algorithm performs better on training data than it does on out of sample data. So the overfitting is something to be mindful of. And here's an example, right? We can literally visualize decision trees as trees and label every decision point. So we start out, is the length of the animal greater than 50? Yes or no? Okay, that's a decision point. Are the eyes blue or not? Yes or no? See how each decision point is a binary, But with this decision tree, we could produce multiple outcomes. Are the eyes blue? No. Is it a carnivore? Yes or no? Or if the eyes are blue, does it have 4 legs or not? I have no idea why the green right here says red. Don't know. We might need to swap out the diagram here. But see how high up, how close to the start the decision point is, how significant that measurement is in classifying things. So this classification, if the length of this animal is greater than 50, is going to make it a better prediction on larger and have a larger impact than if something is 4-legged or not. But see how the deeper we get in the tree, we get more detail, right? So your decision points that are further up the tree have more impact. The decision points that are farther down the tree are dealing with more and more fine and minute layers of detail. And yeah, trees are pretty cool because with tree-based algorithms, we can produce plots just that look like this, probably that look better than this, because you'll have better typography, where we can explain what the model is doing, which is really, really important, right? It's not just, hey, how fast can you get to a model, but does your model explain things reasonably? Can you put your model on the stand? If that classification algorithm is determining if somebody has a credit risk or not, can we take that model and put it on the stand and say, are you discriminating against protected classes with this mortgage application or the credit card application, right? Really, really, really valuable to be able to interrogate our models and understand why they're making certain decisions. Okay, there's an ethical component here, not just a technical component. Random forests are very, very similar to decision trees, except that they are a whole bunch of trees. That's why it's called a forest, and there's some randomness involved. That's I know that sounds kind of obvious, but where the randomness is involved is at each decision point. There's a little extra randomness with a random forest, and we're not building one tree, but we're building many, many, many trees, and we can control how many trees we build in this forest. And the outcome will be an aggregate of all of the trees. Okay, we have a specific lesson on random forests, but it's a type of something called an ensemble algorithm, where it's not just one single algorithm, but there's multiple algorithms going on. That's what ensemble means, just like a musical ensemble. Okay, pros of a random forest: less risk of overfitting than a decision tree, which is really good because that's decision trees' challenge point. Generally more accurate than decision trees. However, because we're building many, many decision trees and injecting more randomness, there's more computation, which shouldn't be a big deal at all for your laptops, right? But if we're running like a gigantic data set, a 2 terabyte data set in the cloud, the computation costs could crank up, right? And random forests are explainable, but they're not quite as explainable as a decision tree itself, a tree in isolation. Okay. Another algorithm that we'll cover that's very, very popular, it's very powerful, and it's very easy, is something called the k nearest neighbors. And with k nearest neighbors, what it's trying to do is, this is distance based. And yeah, let's look at our little diagram here. K and n. So we want to classify things. In this example, in the upper left-hand side, we have the yellow dots, the green dots, and the orange dots. So we have 3 potential classes: green, orange, and yellow. And if we are trying to classify this new data point, this gray data point here, what k nearest neighbors is going to do is calculates the distance to all of the other data points in each of the different classes, right? So this gray data point here, we will measure the distance between that new data point and all of the existing data points and their labels. And what we find is that the in this specific example, k nearest neighbors goes with the closest set of data points that have the lowest distance, right? Distance is a huge deal. And the nice part about this, you don't have to worry about the linear algebra. That's all under the hood. That's all sklearn doing what it does best, right? It's measuring distances between data points. It's evaluating, basically taking a list and making a number of votes based on how close things are. And the closest cluster, the closest chunk of data points wins. That's k nearest neighbors. The k here, k, is part of the name in k nearest neighbors, but it's also something called a hyperparameter where we can set that nearest neighbors to be 2 or 3 or 4. We can control that. That's not something that's coming from the model itself. So k nearest neighbors, very simple to implement. It's robust to noise, performs calculations just in time, which is a good thing. The cons is there's no magic value of k. We have to come up with that one. There is some computational cost, as with everything. And we're introducing this term, I don't know if we've mentioned it before, the curse of dimensionality. The distance can break down in very high dimensions. So if we have 2 columns in our data set, like size and color, that's a low dimensionality, right? But if we had 1,000 columns describing a data point, that's very high dimensionality, right? Or 100 columns of features, and that negatively impacts our performance. Okay. Let's see. Support vector machine and naive Bayes. Okay, cool. Two other algorithms. I don't think we have it. Yeah, we're not going to get into them in the lesson, but they're once you learn one kind of model, it's very, very easy in sklearn to use a new model. Very, very easy. A support vector machine is a classifier. It's very, very popular. And what a support vector machine is going to do is try and it will draw a decision boundary, and that decision boundary can be straight or curved. Usually a SVM is getting some sort of curved decision boundary. And what it's trying to do is maximize the distance between the decision rule and each data point, right? Try to get the highest amount of margin between each one of these, so that the decision rule is not laying on a specific data point if it can help it. It's really what an SVM is trying to do. Okay, and yeah, here's a good thing for support vector machines. They are effective in high dimensional spaces. So where that k nearest neighbors is falling down in higher dimensional space, we don't have to think fancy math with higher dimensional space. We're just thinking lots of columns in the data frame, lots of features, lots of predictive features, right? SVM is very memory efficient, but it doesn't provide probability estimates, right out of the gate. And then another classifier that you may have seen before or may encounter is something called the naive Bayes classifier. And it's not naive in that you can't take it to a bar, right? And it's going to get taken advantage of, right? What the naive here is meaning is that there is an assumption in Bayes' theorem that assumes independence between every single pair of features. That's what's naive. And we know that's not going to be the case, right? Because if we're classifying, if we're trying to do classifications of like a churn or not, we know that more features of telco usually is trending with higher bills, right? People aren't paying less for more features, so those aren't independent features. So that's really the cost of naive Bayes. However, the biggest upside to naive Bayes is that it can be pretty effective in small data sets as opposed to gigantic data sets like thousands or tens or hundreds of thousands. Naive Bayes can do pretty well with hundreds of data points. Okay. But yeah, keep in mind that naive means it fundamentally assuming that every pair of features is independent, which generally that's not the case in reality, right? Cool. We bring up some of these models that we're not going to specifically cover, like naive Bayes, support vector machine, just because you're going to see them, and that may be something that you want to try out on a project or as a kind of an above and beyond. We'll have a lesson on logistic regression exercises, decision tree, random forest, and k-nearest neighbors. And once you get the pattern from these, which is like find the library in sklearn, train your model, and then evaluate your model. It's kind of lather, rinse, and repeat. So you can feel free to use other models if you would like. So what we've covered in this module is an intro to classification, and in that we've talked about the 5 kinds of questions our data science methods can answer. Specifically, we spent a good amount of time talking about supervised learning and what that means and what the big goal is. And the big goal with any supervised learning is learning the rules. And really, when we're talking about different models, and we saw this with sklearn and those classification examples, these different classifiers, there's not one that's good for everything, right? You see each one of these classification algorithms takes a little bit different of an approach, right? But being able to go into your toolbox and say, oh, my decision tree is overfit, how do I fix that? Or that's something we're going to be building those real skills doing. So we're drawing boundaries, or actually the models are drawing boundaries. And this is totally an oversimplification, but you can see based on other very real classifications that the models are just trying to figure out how to do the best that they can. Each different model is trying to make accurate predictions and minimize the misses and minimize the false positives. And we're going to talk quite a bit about that, and quite a bit about we have an entire module on how to evaluate a model and see if a model's any good or not. Because models are representations of reality, but they are not reality, right? So we need to understand what our trade-offs are and what that representation will give us and provide for us. So there you have it, folks. That is our overview of classification. As we proceed forward through the rest of this curriculum, the next lesson will be data acquisition, which you'll see the data acquisition, data preparation, data exploration. We're going to repeat this process in every single one of these, every single one of the new modules, so that we're not just doing modeling in isolation, right? Modeling in isolation is not going to produce value. It's like building a model airplane. We need to make sure that our model airplane represents a real airplane as much as we can, right? So we'll move into the data acquisition lesson and curriculum, and we'll be going in a pretty linear fashion from here on out.